Alright, in this video I'll be doing a few problems from the review for the final. And this is the review that you find under document sharing in my math lab. This is the one I usually do in class, and it's intended to help you prepare for the final and give you some details and some practice. So on number 32, it says determine the oblique asymptotes of the graph of the function. Now, because this one is top heavy, or the degree in the numerator is greater, we don't have any horizontal asymptotes, and in this case it turns out we have an oblique asymptote. And the way we find it is we just divide the numerator by the denominator. So since we're dividing by x plus 3, that's a linear binomial. It's got a 1x here. And that's the kind where we can use synthetic division. So I'm going to use synthetic division with -3 here. And it'll be 1, 4, and -1. And so we would drop the 1. And then we would multiply these two numbers here. And we get -3. In columns we always add. So 4 and -3, we're going to get 1. And then 1 times -3 is -3, and when we add we get -4. And so our answer here is actually, let's see, we're dividing an x squared or a second degree polynomial by a first degree polynomial. The degree is going to drop 1, and so this is 1x plus 1. And so our oblique asymptote will be y equals x plus 1. Alright, and we'll just go ahead and stop there. Let's go ahead and move on to Gaussian elimination with back substitution. So I've got to go a few pages down here. Whoops, too far. Alright, so on number 46, it says solve the system using Gauss-Jordan elimination or Gaussian elimination with back substitution. Now, because we don't have a lot of time, now this semester things were even different, but I usually focus on Gaussian elimination, and I'll mention Gauss-Jordan elimination, which just takes things a little further with matrices. So I'm going to do the Gaussian elimination with back substitution. So the first thing I would want to do is write the corresponding matrix for this system. Now, what we want to do is get this matrix in this form here, where we have 1s on what we call the main diagonal, a 0 below the 1 there, and then numbers elsewhere. So there's 3 types of row operations we can do to get the matrix into this equivalent, more basic form. And so what I really need is, the way we want to start is I want to get a 1 in this upper left-hand position. And this one's a little bit, it takes a little more work than a lot of them. Normally one of the 2 rows will have a 1, and so it's pretty easy to get that 1 where you need it. So remember what we can do. We can switch 2 rows. We can multiply or divide a row by some number other than 0. And then we can multiply a row by some number and add it to another row and replace that row. And so we'll do each of those. Let's go ahead and get started. Now, what I'm seeing here is if I want to get a 1 here, I can see that 3 minus 2 here would give me that 1. Or the way I would write it is row 1 plus negative row 2. That's the same as subtracting row 2. And that's going to be our new row 1. And so it'll be 3 minus 2, you get 1. 2 minus -3, well, that'll become 2 plus 3, which is 5. And then 6 minus -9, that's going to be 15. And then let's go ahead and rewrite the second row. And so now that we have this 1 where we need it, we're going to use that 1 to get a 0 right below. And so this is the case where we're going to want to multiply the first row by some number and add it to the second row so that we can get a 0 in the first position. So we want to multiply by -2. If we multiply -2 times row 1 and we add that to row 2, and that becomes our new row 2, then we'll get the 0 that we need. So I'm going to go ahead and multiply each of these numbers by -2. -2 times 1 added to 2 is going to give me the 0 that I want. Oops. So notice I just went ahead and wrote the first row. That's not changing. So we did -2 times 1. We added that to 2. We got 0. Now we're doing -2 times 5, which is -10. Added to -3, we get -13. And then we have -2 times 15, which is -30. And -9 gives you -39. And so now that we have this one and the 0 below, we're going to move down the main diagonal, and I need to get a 1 here. And the easiest way to do that, notice 13 and 39 are both divisible by 13. In fact, I want to use -13 because I need a 1 there. So really, I'm just dividing row 2 by -13, and that's going to become the new row 2. Now, we don't normally write this operation or explain what we're doing this way using division. We usually use multiplication. We call this scalar multiplication. So basically, we're going to multiply by the reciprocal, -1/13 times row 2, and that becomes the new row 2. And really, again, that's equivalent to just dividing by -13. So the first row doesn't change, and we're just going to divide 0 or multiply 0 by -1/13. That's still 0. -13 divided -13 is 1, and -13 or 39 divided by 3 is, -39 divided by -13 gives you 3. All right, so finally we have what we wanted. We have these 1s on the main diagonal and the 0 below. This is in the form that we want, the desirable form that I was talking about over here. And so now we're ready to go ahead and write the system. So it'll be x plus 5y equals 15 and y equals 3. And notice we can use what's called back substitution and plug the 3 in for y here. And so we have x plus 15 equals 15. If you subtract 15 on both sides, you get 0. And so now we have solved our system. We have 0 for x and y is 3. So the solution is the point 0, 3. All right, let's move on to the next problem. All right, so here again I'm going to use Gaussian elimination with back substitution. And I want to get this matrix in this nice form that looks like this, where we have 1s on the main diagonals, 0s below, and numbers everywhere else. And then once we get it in that form, we'll use back substitution to solve the system. So we're basically coming up with an equivalent system that has the same solution, but it's easier to solve. And so let's go ahead and write the corresponding matrix for each of the rows here. Well, the corresponding matrix. And so you should get this matrix here. Now notice I already have a 1 in the upper left-hand corner, so I don't need to worry about that. But I want to use that 1 to get 0s below. So I want to multiply the first row by -2 and add that to row 2. That way I'm going to end up with a 0 in this position here. And that's going to become my new row 2. And similarly, working with these two rows, I'm going to multiply the 1 by -5 and add that to row 3, and that's going to become the new row 3. So again, you can see I'm using this 1 to get 0s below. So let's go ahead and do that. So the first row doesn't change. So we're going to multiply each of these numbers by -2. And so, and actually I probably shouldn't do it there. I should do it up here. Okay, so -2 times 1 is -2. And when we add that to 2 here, we get the 0 that we want. -2 times -1, that's here, is 2. And when we add that to -3, we get -1. -2 times 1 is -2. Added to this 4, we get 2. And -2 times -4 is 8. And when we add 8 to -15 here, we're going to get -7. All right, so let me get my eraser. Now you don't have to write this the way I'm doing here, but for some people it's helpful. So now I'm going to multiply the first row by -5. So I'll multiply, whoops, let me get my pencil. Multiply each of these numbers by -5. I'm just multiplying the whole first row by -5, and I'm going to add that to row 3. So -5 times 1 is -5 plus 5. We're going to get 0 in the first position, which is what we were trying to do. -5 here times -1 is 5, plus this 1 is going to give us 6. And here we're going to have -5 plus -2, which is -7. Here we're going to multiply, we get 20 added to 12, and we get 32. So we got the zeros below the 1 that we wanted. And so now we're going to move down the main diagonal, and now we need to get this -1 to be a 1. So that's actually going to be pretty easy. The easiest way would be to just multiply that row by -1. So we're going to do -1 times row 2, and that's going to become our new row 2. And so let me go ahead and rewrite the matrix, and the only thing I've done is change row 2, where I just multiplied each of these by -1. I should say each of these by -1, and so now our signs are the opposite. But the thing is, now we have a 1 here, and we're going to use that to get a 0 below. And so I'm going to want to multiply that 1 in the second row by -6. So -6 times row 2, and we're going to add that to row 3, and that's going to become our new row 3. And so the first row doesn't change. The second row doesn't change. And so now let's go ahead and multiply each of these numbers by -6. So -6 times 1 here is -6. Added to 6, we're going to get the 0 we want. By the way, we could also multiply 0 by -6, and that's 0 added to this 0. And so we do get a 0 in the first position. And we also, again here, -6 times 1 is -6 added to the 6. And we do get the 0 that we wanted there. And -6 times -2 here is 12. And a -7 is going to give us 5. And -6 times 7 is -42. And when we add that to 32, we get -10. So now we're almost there. We just need a 1 here, because we got our 1 here with zeros below. Then we got our 1 here and a 0 below. And so now we continue down the main diagonal, and we need to get a 1 where the 5 is. And so really, you can see 5 and -10, all we have to do is divide by 5 here. So I could write it as row 3 divided by 5, and that becomes the new row 3. But again, we normally write it by multiplying by the reciprocal. 1/5 times row 3 becomes the new row 3. Again, that's just equivalent to dividing by 5. So I'm going to rewrite the first two rows, And I'm going to divide everything in the last row by 5, and we get 0, 0, 1, and negative 2. And so finally, we're ready to solve the system. We can go ahead and change back to the equation form. Notice z is negative 2, so I can replace z in the middle equation here. I get y minus 2 times negative 2 equals 7. This becomes y plus 4 equals 7. And we'll subtract 4 on both sides, and we get y is equal to 3. And so now we can go back to the very first equation. Again, this is why we call it back substitution. We're kind of going backwards, and we're doing substitutions. So we have x minus y plus z is equal to negative 4. We're going to plug in 3 for y and negative 2 for z, And so we're going to get x minus 5 is equal to negative 4. And when you add 5 to both sides, you get 1. So our final solution is the point, or the ordered pair, not ordered triple, since we have 3 parts, 1, 3, negative 2. By the way, you could easily plug 1, 3, and negative 2 into each of these 3 equations using a calculator or doing it in your head, and you can see that it does work in all 3 equations. Alright, I do want to cover 48 real quick. This one should go pretty fast. So in the bottom line here, or row, we have 0x plus 0y equals 7, which means 0 equals 7, which is a false statement, which means or indicates this system has no solution. So normally what's happening when you're solving a system, you get a row like this bottom row, and at that point, you know you have one of these special cases where you're not going to get a single point or order triple as your solution. In this case, there is no solution. Although in this kind of system here, you would have an ordered pair as a solution normally. Let's look at B, where we have a row of zeros. That tells me that there's infinitely many solutions, but that's not really all that helpful. It doesn't even give me one solution. And so what we do is we write the equations, and we use what's called a parameter. We could solve for the 3 parts of our point, our order triple, using x, y, or z. Normally we like to use z. It tends to be easier in a situation like this. So notice in the second equation, I can solve for y in terms of z just by subtracting 4z on both sides. So z is just going to be z. We're going to use z to represent z. Y would equal negative 4z plus 5. So we've solved y in terms of z, and we need to do the same thing for x. So it's a little more work, but we just have to plug in negative 4z plus 5 for y. So we have x plus 2 times y, which is negative 4z plus 5, minus 3z is equal to 4. So let's go ahead and distribute here. It'll be x minus 8z plus 10 minus 3z equals 4. We have some common or like terms there. Let's combine those together. We get x minus 11z plus 10 is equal to 4. And so finally, I'm going to add 11z to both sides and subtract 10. You're going to get x equals 11z minus 6. And so our final solution is 11z minus 6, comma, negative 4z plus 5, comma, z. Now, just to show you how this works, if we wanted to actually find one of the solutions, you could let z be anything. What if I let z be 0? Then plugging 0 in here, negative 4 times 0 is 0, plus 5, you would get 5. And putting 0 in for z here, you'd get 11 times 0 is 0 minus 6, that's negative 6. And so this is just one of the infinitely many solutions. And, oh my goodness, I'm falling asleep. So just pick different values for z, and you can see other points that would be solutions. All right, so that's it for solving systems using matrices or Gaussian elimination.